Hi, my name is Robert Kaman, and my project is the quantification of thermohydrogen refined microstructural features in additively manufactured Ti-6-4. So Ti-6-4 is a titanium aluminum vanadium alloy that has a wide range of achievable mechanical properties and is desirable especially in the aerospace industry because of its high strength to weight ratio. And the microstructure that I'm looking at has been developed by people at ARL, and it's got very fine grains because of the hydrogen thermal treatments that it's been put through that allow greater amounts of undercooling and ultra fine grains to form. But it's a very difficult structure to analyze in terms of its microstructure because it's two-phase. Its grains tend to be very complicated shapes, and there's no universally accepted method for segmentation or shape analysis. So the goals for this project were to develop methods for quantitative microstructural analysis of this microstructure, automate them, and then test their accuracy. So the first leg of this project involved segmenting these microstructures, which proved to be pretty difficult. It's got two phases, a gray HCP alpha phase and a white BCC beta phase. And the first thing I did to segment them is I used a machine learning program developed by some people in New Zealand to segment these phases and then detect alpha-alpha boundaries as well as alpha-beta boundaries besides that as step 2, and then to combine the two and further process the image to have an accurate representation of the microstructure. So once this microstructure has been segmented, it is important to describe the microstructure in quantitative ways. So one semi-standard way to do it is draw a bunch of lines across the image and look at the lengths of intercepts between the regions that we're interested in this case, mostly those dark gray alpha grains. And for each intercept that a line includes within a grain, you add that to a bin, and that's your grain size distribution. Another non-standard metric I was looking at was local thickness, and this involves, after segmenting the microstructure, looking at every pixel and finding the largest inscribed circle that includes that point. And this can be visualized on the right. You can see either as a heat map or a 3D plot, where for each pixel within the region, there's an associated thickness value. So both of those metrics were used to try to define microstructure property relations in this material. We had 10 samples of this hydrogen refined Ti-6-4 and 2 different AM fabrication methods. I will not talk about processes here because the point of this study was microstructure property relations. And in general, you can see all these have very similar values. So after defining some of these microstructure metrics, they were correlated here in this correlation matrix with some number of properties, including yield strength, hardness, elastic modulus, and ultimate tensile strength. And because all the microstructure metrics had pretty similar values, there are no significant microstructure property correlations. So the rest of this project I dedicated to describing these microstructure metrics more accurately, because there are subtleties that do become really important. And the first way I try to quantify the difference between these, I used Voronoi patterns as synthetic microstructures to analyze. These are randomly generated points that result in randomly generated microstructures that tend to look vaguely like real microstructures with there are some subtleties, but it's roughly the same. So I varied the point density, and I took a look at how each metric described the size of each grain. The linear intercept method had averages that are more consistent over varying point densities, but something interesting is they're both pretty darn good. On the left, there is a graph that correlates mean thickness of each sample with the mean intercept value of each sample, and they definitely follow a linear correlation that is greater than that expected for a circle, but less than a one-to-one correlation. The next way I tried to describe these microstructure metrics was looking at how they describe multimodal microstructures. So both equiaxed and high aspect ratio grains that are in a multimodal distribution. What's interesting here is that the thickness kernel density estimation plot describes more precisely the area amount of large grain and the area amount of small grains, whereas the linear intercept method does not. There's a little peak around 150 pixels for the equiaxed microstructure, but for the most part, only its average is a good metric of grain size, and the distribution has less to do with the actual microstructure. It's a similar story for the high aspect ratio microstructure there, but because the high aspect ratio grains are present in the microstructure, the linear intercept method actually describes a count of far higher for the small grains, and so the mean for this distribution would be much lower. So if you were going to choose a number to describe the grain size, linear intercept method would do fine, but if you had to choose a type of distribution to describe the grain size, thickness describes that much more precisely. And there's no hidden information there like there is in the linear intercept distribution. Because these thickness distributions describe the thickness of the grains so precisely, it makes it much easier to threshold these images, because really all it is a 3D plot. So you can threshold this image, and you can very easily take a look at what the volume percentages are for grains of certain thickness. So in this multimodal microstructure, about 50% by volume of the microstructure has a thickness less than 36 pixels, and about 13% is greater than the half of the maximum. Now this is super cool, because this ends up being a super important metric in TIE-6-4. You know, you tend to have equiaxed alpha grains as well as high aspect ratio smaller grains. So because each image segmentation is not perfect, it was important to look at how imperfect segmentations affect each microstructure metric. So what I've done here is I wrote a few methods to iteratively make a microstructure appear less well segmented. Then I measured its effect on the deviation of grain size as defined by each metric, thickness and intercept. So these images describe that process. On the left is a regular Voronoi pattern. On the right is one that's gone through 100 iterations of adding white and black lines to represent an image that has boundaries that are undetected and point-like inclusions that pretty frequently show up under SEM images. So there are three methods that I used to make the microstructure look like a poor segmentation. The first one only adds point-like inclusions, and as it turns out, thickness is relatively sensitive to this. It ends up at minus 10% deviation, whereas intercept method ends up at negative 4% deviation. The second method involves simulating deep scratches and poor boundary segmentation. It's sort of interesting here because each metric has opposite sensitivities. The local thickness has a negative deviation, but the intercept method is more affected by the removal of the boundaries and has a positive deviation. The third one is more likely what I would see in a poor segmentation of TIE-6-4, is made to represent missing boundaries, in this case probably missing alpha-alpha boundaries, point-like inclusions, but at a lower density. It's very interesting here because the linear intercept method saw very great positive deviations because of the removal of the boundaries. Local thickness was not affected by this very much, and this is partially because local thickness means are not very much affected by low percentage of boundary removal, and also for the amount that is affected, this is balanced out by the inclusions, so the mean is just happens to be almost a net zero mean deviation. For this reason, I think local thickness is a far better metric, far more consistent metric when you take into account poor segmentations, if those segmentations include relatively conservative detection of grain boundaries, because that's what this third method is made to represent. So that was a fairly good summary of my project. I appreciate your time. Let me know if you have any questions. Thanks.